So up until now, we have covered up to generics, and this time we will start functional programming. And this is one of the most important topic in our Java language. This one is more important than, you can say, generics, and we can also say this one is bigger than our collections framework. So we will start functional programming, and in this one we have 10 chapters. So we will start with lambdas, and then we will cover streams, then we will cover optional class and parallel streams. So first we will cover lambdas, and this one is very important. Okay, so hello from functional practice. We are getting suggestions. So back in 1995, when our Java came, then our Java was purely object-oriented language. So everything was objects and classes. So let's say if we wanted to pass a piece of behavior, we can say anything short something by length. Okay, like let's say arrays of strings, and we want to sort them by their length. Okay, so we cannot pass that behavior with the help of just object oriented programming style. Okay, first we had to wrap that in an object, we had to create one class, okay, something like that. We had to implement one interface or anything, and that we can say one boilerplate even for one simple thing. And almost 2 decades, that was the only way. And then in 2014, we got our Lambda expressions that changed everything. Okay, so in Lambda expressions, we can store something, we can say behavior, in our variable. We can pass that variable to any method. We can also return that from any method. Okay, we will see in depth. So this one is just introduction to our lambdas. Okay, so lambdas are just basically a piece of executable code that can be passed around and executed later. Okay, so we got this suggestion. Let's take this. So we can move this one around like a string or an integer. Okay, that can be anything. Okay, so in this one we will see what actual problems lambdas solve. Like we discussed this one, but we will see. So then second one, we will see what lambdas are at our language level. We will also see functional programming. Also, we will see functional interfaces. Okay, and why lambdas need them, and what happens if an interface has two abstract methods. We'll also see. On this one is just simple thing. So let's start our first chapter, which is introduction. Lambda expressions introduced in Java 8 represent one of the most significant changes in the Java language, and they bring functional programming concepts to Java, allowing us to treat functionality as a value, something that we can pass around, store, and return from methods. Okay. This seemingly simple addition fundamentally changes how we write Java code, and this was very necessary step in order to survive in other languages for Java. Okay. So the paradigm shift. Before lambdas, Java was purely object-oriented programming. Everything revolved around objects and classes. If we wanted to pass behavior to a method, and we will see this one, had to wrap it in an object, usually through anonymous inner classes. So this one is our old way. Let's say we have one in this one. Let's say we have one list of strings, and we can name this one names. Okay, and we can create, or we have to import this one, that's fine. Now here we can create, or we can initialize with some initial data. Now let's say we have to sort this string based on length. Okay, so how we can do that? We can do this one collections.sort, and we can pass this one our custom comparator, or basically we can say anonymous inner class. Okay, so we can do that collections.sort. Even this one is the very simple and very short syntax for our oops. Okay, now we can import this. Now here what we can do, names, new comparator. Okay, we are getting one suggestions. Let's take that. Override. Okay, so in this one, basically we will be returning the length based sorting integer dot compare a dot length. Okay, so this one is fine. So this is how we had to do this one without our functional programming or lambdas. And this one is just one simple thing like sort these by their lengths. Okay, and if our logic is complex, then that code will be long. So we are here, or we are getting here suggestions that can be replaced with lambda. So lambda's approach will be more effective here. Here we are doing one class declaration, okay, then writing some annotation, then method signature here. Then here is our actual logic that is we want to work, okay. Then closing these kind of things. So we have so many lines. And if you will see in other languages like Python, JavaScript, even C Sharp, okay, they have their first class functions. Those do these kind of things in just one line. So Java also adopted that kind of design. And now we can do these things just in one simple line. So collections dot sort, even we are getting one suggestion. And this one is just lambda, so we can take that. Can be replaced with comparator dot comparing int. Okay, so we have seen that comparing int, but here we will discuss lambda. So this is fine. So now let's see. This one is our new way, lambda expression, same behavior, just fraction of code. So lambdas are not magic. Under the hood, lambdas are still converted to objects, but you write less and the code reads better. Now let's understand what exactly is a lambda. A lambda expression is essentially an anonymous function, a function without a name that you can define inline. It has parameters, arrow operator separates parameters from body, and body the code to execute. So we have this syntax, and these are our parameters. Then this one is arrow syntax and our body. So we can think of lambdas as behavior literals. Just as hello is a string literal and 42 is an int literal, we can see this one is a behavior literal, okay, that do something. So here you can see, we can understand this statement more better, okay, like this one. So let's say we have this string value. So s equals to hello, okay. So here our string value stored in one variable, right? Also we can store like integer. So how we can store behavior in some variable, that is one thing. So let's say we will see this thing in our later chapters. So function string, let's say string, this one is one just a syntax. So we can import this and we can put this one, let's say behavior equals to s1, okay, s1 to uppercase. We can also add here anything. So this one is our behavior and we can use whenever we want. Let's see how we can use that. Let's say we want to print, then b dot apply. So we have this method for this functional interface. We will see this one. So before lambdas, Java had only data values like this, but after lambdas, Java also has behavior values, okay, like this. Now, functional interface is the foundation. Here's the key insight. Lambdas don't exist in isolation. They need a type, and that type is a functional interface, okay? this one is very important keyword. So a functional interface is an interface with exactly one abstract method. And we have discussed that. So SAM, single abstract method. This single method defines the shape of the lambda, what parameters it takes and what it returns. Okay. So let's say you have one interface. In that one, you have only one abstract method. So we can say that interface is functional interface, but you can also put that annotation as well, so that if you try to implement two abstract methods, then you will get one error. Okay. Now let's see why lambdas need them. Okay. So why lambdas need functional interface, and also we will see what is the type of lambda. Okay. So what's the type of this syntax? We can write here A, B, and this one. So what's the type of this thing? And we can say this one is functional interface. Okay. So a lambda doesn't have its own special type. Instead, this automatically matched to an interface that has exactly one abstract method. So if you open this one, then you can see here, this one is marked with functional interface and it takes two parameters, and those are generics. We have just finished our generics topic, so that will be understandable now. And we have this one as our, this one is our one abstract method, and its return type is its second parameter type that we have to pass here. Okay. So this one. So this second argument will be your return type. Okay. And if you put here integer, then you will get one error, because this time your syntax will not match. Okay. Because your second argument is your return type, and you are returning here string, but here you are mentioning integer. So that is a one problem, and this one is one type mismatch. So if your this function is not functional interface, then you can define one other method, okay, in which you can define some other method signature, okay. But in this case, we only have this one, so we must match exact method signature with this one, okay. So this is why our lambdas need functional interface, because of like finding what method we are actually trying to call, okay, or we are trying to provide body. So we can define our own functional interfaces as well. You can see this annotation, and here we can define, let's say, public interface calculator. We can define anything, calculator, and here we can define one single abstract method that can be anything, let's say calculate, and this one. So we cannot do that. That's fine now. So we defined this one, and now we can call this here. This one is just simple. So calculator, and add equals to, let's say, store that a, b, and we will return a plus b. Okay. So now our lambda will match these one to our this functional interface. Okay. Okay. And now what's the problem? B is already defined in this scope. Okay, here. So we can just comment this one. Now this one is fine. Okay, now we can just compile this one. And we can just run this one. So you can see we got 3 here. So this is how we can define our own functional interfaces and use lambdas on them. So basically, this one method rule creates a one-to-one mapping, and our lambdas parameters match the methods parameters. Okay. So like here we are passing two integers, then this one will match to this one, like this functional interface. Okay. And our lambdas body provides the methods implementation. Okay. So no ambiguity at all. Now let's see what is allowed beyond just one abstract method in this functional interface. So we can write so many things. And first one is, so this one is our one abstract method, right? Second one, we can write default methods. Okay. So we can write here default, let's say anything, string, um, as int a, int b, so return hello. So that's also fine. Let's take suggestions. Okay. So we can define here default methods. So they must have implementations. Okay. We can also define here static methods, int add, return a plus b. So our static methods belong to the interface, not instances. Okay. And then we can also have some methods from our java.lang.object class, like toString equals hash code. Okay. Object, we can also define here toString. So we can also do that. And this one will not count. Same for equals. Okay. So these things we can define other than just one abstract method. So we have just clear role, one abstract method that isn't from our java.lang.object class. Okay. So if you remove this one, then you might declare two abstract methods. But if you try to do that now you will get one error, and that is, you can see here, multiple non-overriding abstract methods found in calculator. Okay. But if you comment out this one, now you are good. Correct this one. So now this one is fine, but now you cannot use lambdas, right? Okay. So now let's see next thing. Why a single abstract method? That's fine. Functional interface annotation. So what this one does, compile time validation. If someone accidentally adds a second abstract method, the compiler throws an error. Okay. Documentation, IDE support. So what's allowed in functional interfaces? You can see default methods we can add, static methods, and methods from object. Okay, these four things we can do. How lambdas connect to interfaces. Okay. So let's understand our matching process. So when you write a lambda, the compiler determines the target type. Okay. So we can say target type is the type of the lambda is determined by where it's used, not by the lambda itself. Our same lambda body can match different interfaces depending on just context, okay, where that is used. So you can see here, target type is comparator. So if you define this one, so our compiler will match, let's say this comparator is our target type, and its abstract method is, you can see, if you can copy this one, then you will see basically here, its abstract method is compare. Okay. And that return int. Okay. So this one takes two parameters and will return int. So we match our interface abstract method. So this one will compile. Okay. And later we will see another functional interface, that is by function. So this one takes three arguments. So let's say string, integer. So this one will return this type. So here our compiler will match this syntax. It has one abstract method, that is apply. You can also open this one. You can see here, okay, your third argument will be your return type. So that's how our compiler match. Okay. So what if our compiler can determine the type? Then we will get one error. And first one, our target type of lambda must be a functional interface. Okay. So let's see. So this is called target typing. The type of lambda is determined by where it's used. Now, real world lambda uses event handling, collection operations, thread creation. We will see threads, and we will be having a lot of discussions on this one. custom behavior injection. You can also see that. Then we have common pitfalls. So that's fine. Okay, so lambdas under the hood. Okay, so before that, let's see some things. Okay, so one thing is clear that our lambdas only work with our functional interfaces. Maybe you can ask that if, let's say, we have one abstract class that has only one abstract method, so can we work with that in our lambdas? So the answer is no. Okay, only functional interfaces, because our lambdas cannot target our abstract classes. So let's say if you write, first let's correct this one and remove this one. So now let's say you want to create one abstract class processor, abstract string process, and this one. So now we cannot work with this one. Okay, if you try to do this one, let's say here, so we got one suggestion for calculator, we can do that, but can we do that processor p equals to, let's say, s dot to upper? Even we are not getting suggestions, that means this one is wrong. Okay, so we cannot do that. Okay, so this one is the problem, and the reason is abstract classes can have constructors. Okay, so we can define here constructors, we can also define here some fields, okay, some mutable state. So if we allow lambdas to target them, then we can create objects with invisible state management, and our JVM can do same kind of optimization. All right, now let's see lambdas under the hood. Unlike anonymous inner classes, lambdas don't always create new class files. And we have seen that if we use anonymous inner classes, then we will get new files, okay, dot class files. But in case of lambdas, we don't get that. Okay, we have even used here, we did not get any class. So let's see again. If we delete this one, we can also delete this. We can also delete this. Okay, so if we compile this one, then we will not get any class for this one. Okay, we will get one class for our functional interface. We will get one class for our calculator and also for processor. Okay, so every explicitly declared top level or even nested classes, interface included, okay, they will get their own .class file when compiled, but we will not get our class for this one. So our compiler will generate those classes so that our JVM knows something like our this interface exists. So if we clear this, so if we run this one, then you will see we got here this processor class. Okay, that's fine. We got here this calculator class for this interface. We got this functional practice class for this. So this one, functional practice, will be our main driver class. Okay, and this one will be our interface, and this is our one abstract class. Now, if we have used here anonymous class, okay, so let's say something like that, new calculator, okay, and here if we have used something like this, so this time we will get one new class, okay, and if you can notice, we got this class, functional interface, then $1. So in case of anonymous classes, we will get these kind of names, okay, in our .class files because they are anonymous, and our compiler put just a number here, okay. But in case of functional interfaces or lambdas, we don't get those class files. And this is the exact reason that our lambdas implementation are fundamentally different, and our JVM can optimize, okay, under the hood. So what actually happened here? Let's discuss just high level. Unlike anonymous classes, inner classes, lambdas don't always create new class files, okay? And we have one mechanism, invokedynamic, introduced for dynamic languages to defer the decision of how to implement the Lambda until runtime. We have some benefits. First one is just performance. JVM can optimize Lambda creation. Okay. So basically, our inside this class, functional practice dot class, our compiler packages our Lambda code into one private and static method. We can say that synthetic static method. And then at runtime, our JVM uses that mechanism we can call one another, that is Lambda Meta Factory, to dynamically generate one lightweight implementation class, and that will be in memory. Okay. So less bytecode, no extra .class file for each Lambda. Flexibility, implementation can improve in future JVM versions. So you don't need to understand invoke dynamic to use Lambdas, but knowing they are optimized differently than anonymous classes explains why they are often faster. Okay. So this thing is very important. If in our future versions, JVM will find a new way to implement our lambdas, then our previous code will also get advantage, okay, from that implementation directly. Okay, and one another fundamental difference between our lambdas and anonymous inner classes, you can say any class, is that our lambdas don't refer this. Okay, this, like I'm talking about keyword. So this one is very important thing. You can see here, maybe we can create something. So let's create one example we can understand better. So let's say we have one class, and that is we can put here lambda anonymous. Okay, so here we have one method that is, let's say, public void test, we can say. So in this one, we can create one anonymous class, okay, that will always holds reference to our this, okay, enclosing, basically enclosing this. So let's use one different thing. So runnable r equals to this, that's fine. This one is one lambda. So what we can do is new runnable, we can do here override, and okay. So our this class will always holds one reference to our enclosing this, okay, even if this does not have anything from our outer class, okay, but still this one will hold one reference to this one, so that our garbage collector cannot collect some code, unused code, okay. If you put here one R2 using lambda, so this one only capture what it actually need, okay. So we don't have any outer reference even to this one. And here you can see we can have some reference to this thing. We can put lambda dot this dot test. So in anonymous class we can do that. Okay, so in this one what we can do, we can print one name, okay. We can print here system dot out dot print ln. You can print here this dot get class dot get name, or maybe get simple name. And if we try to do this one from lambdas, then you can see if we need multiple statements, then definitely we need these brackets. Now we can call these two behaviors here. So r dot run, r2 dot run. And if we call this from here, let's say new, okay, test. Now you will see that what we will get, clear this and just compile this. And now we can just run this one. So in this one, you can see hello from functional interface. Okay, that's fine. Then hello from anonymous class. And here we got hello from lambda. Here we can understand more better now. Calling this one dot get simple name or dot class on anonymous class, we will get empty string. Okay, so that's why we got here empty line. But if we call this one on lambdas, then lambdas don't introduce new level of scope. Okay. So they will just point to the enclosing class, which is in this case Lambda Anonymous. So we got this name. And here, this one will point to our this runnable instance itself. Okay. So this is one difference. Now we can move forward with our summary part and we can move to our next chapter, which is Lambda syntax and patterns.